Well, at this point, it probably seems like we're on top of the world because we've got an analytic method for solving differential equations, and we can also take a look at their slope fields to really understand what all solution curves must look like. But there are some times that we run into problems where we're trying to come up with an approximation or come up with an answer, and we don't have the techniques to do it. So there's this third method, this third technique of solving differential equations called numerical techniques. And these are sometimes referred to as computer or approximation, or there's a bunch of names for them. But basically what we're going to do is we're going to approximate solutions and curves. And that's what the numerical method's all about. Now, I don't say the numerical method because there's more than one. The one that we're going to focus on is called Euler's method, and it's probably the most well-known. It's kind of the entry-level numeric technique, and that's the one that we're going to focus on in this class. So what I want to do is start off by taking a look at a differential equation, which on the surface you might recognize as being autonomous. Excuse me, not autonomous, but dependent only on the independent variable. So this is just a function of x. And so on the surface you might think, oh cool, I know how to solve those. Just integrate both sides. The problem is integrating this thing with respect to x is a real pain in the butt, because it turns out that thing is not the derivative of any elementary function. So there's no natural log, there's no exponential, there's no polynomial, there's no sine or cosine or arc cosine or hyperbolic cosine or anything like that that you've seen before that has this as a derivative. So we're in a bit of a pickle. So we might hop over into Maple and say, no problem, Maple can solve it for us. So what do we do if we desolve? And then I'm just going to do differential equation y of x comma x, and that's equal to exp, or e to the power negative x squared. And so I say to Maple, hey, solve that for me. And Maple thinks about it for a second and says, okay, it's this. And it's something you've never seen before. What the heck is ERF? Well, it turns out that's the error function of x. Now, you've never heard of that before, probably. And if you have, you probably don't know where it comes from or what to make of it. So this is an example of kind of a dead end for us. We don't have a technique for being able to get to this as a solution, let alone understand what it looks like. If you wanted to, you could plot what this thing looks like. You could plot the right-hand side of 1. And what did I do? Unlimited delimiters. Oh, darn it, I did it again. I forgot my extra close parenthesis. And if you plot the right-hand side of that, notice it says, cannot determine plotting variable. Oh, that's because I have the constant in there. Oh, whoops. Yeah, I don't want to plot that. Hold on. Let me back this up. I'll do this. Plot that. And I just drop that in there and say, hey, Maple, plot that for me. And it says, no problem. It looks like this. Now, there is no curve that you've ever seen that produces that, or there's no function you've ever seen that produces that. So we're kind of dead in the water. So we don't have a way of doing it, and so that means we don't really know what to do, and so we could try to solve analytically with Maple. But ugh. Right? We wind up with a really ugly looking solution. The other thing that we can do, we can visualize it with a DE plot and approximate it with a numerical solution. Now, the reason I say we could visualize it with the DE plot is because if you remember from the last section, we can hop back over into Maple and say, hey, Maple, I'm just going to borrow this right here. Hey, Maple, will you create a DE plot for us that is this differential equation where y of x is the dependent variable, and we're interested in going from, I don't know, x equals -5 to 5, and y goes from -5 to 5. I'm boring. And Mabel says, sure, I can create a DE plot, and it looks like this. And you probably will recognize, hey, that curve looks like it belongs to this family of curves. And sure enough, it does. It's exactly the shape. So what we're seeing here is we can get a visualization of what the solution must look like, but that doesn't allow us to make very accurate predictions. Even if I threw an initial condition on here and said, what if y of 0 equals 0? Maple says, oh, okay, I can create that solution curve. It looks like this. But it's not very handy for me to be able to make predictions on, hey, what's the value when x equals 1? Kind of eyeball it and say, well, it looks kind of like x equals almost 1, but the graph isn't very good for that. And so that's what I mean when I say we can visualize it with a DE plot, but we're going to approximate it with a numerical solution. And so what do I mean by a numerical solution? Well, it's really just a computer program that we're going to generate and then follow. And so let's consider this example right here, a brand new differential equation. What if we had an initial value problem like this with a DE and our initial condition? Now, this guy right here is not separable. So we do not know how to solve this analytically. So unfortunately, not separable. So we don't know how to solve it. But we're going to use a technique that's going to allow us to predict how this thing behaves and make predictions for what happens when x equals 1 or 2 or 3. And in order to do that, we're going to use our differential equation as kind of a map. And so I'm going to give you the steps that we're going to follow. So the first step that we're going to follow is we're going to start at a given initial condition. And that's going to be a location on the xy plane, right? In this case, we're starting at 0, 3, or excuse me, -3, right? And the second step in our process is we're going to use those coordinates, use the IC coordinates in the differential equation to determine which way the solution curve goes at the IC. Now think about what that's saying. If I plug in an x value and a y value into my differential equation, this is going to spit out the slope at that x and y coordinate. And so, for example, at y or x of 0, or x is 0 and y is -3, that would mean dy dx equals 0 plus 1/5 of y, so that would be -3/5. So this is saying at the point 0, -3, your solution curve is going to be going in that direction with a slope of -3/5. Step 3 says, okay, now move along that slope direction a small distance. That means this is going to be our take a step, right? So we're going to move along this direction, the -3/5 slope line, and in your head you can imagine -3/5 is kind of going down, and we're going to move a small distance. Step 4 says, okay, now that we've moved a small distance in that direction, note your new coordinates. And now that you're at a new place, a new point on the xy plane, you've got a new set of coordinates. So guess what we're going to do? We're going to go back to this step and say, okay, we're at a new coordinate, plug those into the differential equation, figure out what the slope is, and then take a small step, and you keep doing this time after time after time. Step 5 really is go back to step 2 and do it over again. And so what we're going to have, in essence, is a graphical representation of what our solution curve might sort of look like. So in the case of this particular example, if you have x and y, and say you start down here at 0, -3, and you take a step and you go a certain distance that way, and then you take another step in a new direction, maybe it tells you to go that way, and then you take another step in that direction, and then you take another step in that direction, and you wind up starting and stopping. Your end point someplace over here is an approximation. And so what you've done is you've created what looks like a bunch of little line segments, but that's an approximation of the curve. These segments approximate the solution curve from the initial condition. And so we've developed a new method for being able to not find the exact answer, but approximate what that solution curve looks like. And that's what this entire section is about, learning how to do that. And so we're going to see on the next page how it works.